Alright, welcome back to the channel. This is the exponential functions review for Algebra 1 Honors. So number one, given the function, determine whether it is recursive or explicit. Remember that recursive means you start with some value and then you're told how to get to the next value from the previous value. So you have to be told what you start with, and you have to be told how to get to the next one. So when we look at the first function, it tells you that f of 1 is 10 and f of n is equal to f of n minus 1. So some term is equal to the previous term times 4. So that has to be a recursive rule because we're given some information and we're told how to get to the next term. The second function, f of n is equal to 5 times 3 to the n minus 1. That's just explicit because I'm not told what I'm starting with. Separately, like we know from doing these in class that 5 is my initial value and the 3 is the growth factor. The third one, f of 1 is 20 and f of n is f of n minus 1 plus 5. This could be recursive again. And f of n equals 10n plus 2. That's going to be explicit. Number 2, using the geometric sequence 10, 30, 90, 270, and 870, answer the following. Write a function to represent the sequence. So it's geometric. We know it's geometric because when we look at each term, it's times 3. And then 270 times 3 is going to be 870. That should actually say 810, not 870. It's just a typo. But we know it's geometric. So we know that our rule for a geometric is y equals a times r to the n minus 1 power. That's how we talked about it in class. A is the initial value of my sequence, which we could see is 10. So I'm going to use function notation just because it says write a function. So f of n equals a, which is 10, times r. R is my growth rate or my common ratio, which is 3 to the n minus 1 power. Part B says find the 11th term. So I'm going to plug in 11. So f of 11 is equals to 10 times 3 to the 11 minus 1, which is 10 times 3 to the 10th. Use your calculator and we get a value of 590,490. Number 3, Jack is reviewing the change in the value of an investment. Write a function Jack can use to model this data. So the time, it looks like they're not increasing by 1s, we're increasing by 5s. And the investment in hundreds of dollars is going from 0.25, so that would be like $25. Then we go to 0.5, which would be $50, then 100, then 200, then 400. So it looks like we are doubling, but we're not doubling every year, we're doubling every 5 years. So write a function Jack can use to model this data. Since we're using a word like doubling, we have a common ratio. Doubling would be a ratio of 2. We have an initial investment, which we can see is 0.25. So my function would be f of n is equal to, or I'm actually going to use f of x instead of f of n. F of x is equal to 0.25 times my growth rate is 2. I'm doubling, and normally we would just put x, but we're not x would mean that we're doubling every single year, but it's taking us 5 years to double, so it's x divided by 5. We did some of these in class where it was like it takes you cut it in half every 3 years or something like that. So we just change our exponent to x over 5 to show that it's happening every 5 years. Okay. So 3b, we move back up to the top of the other side. What type of function is this? Well, it's going to be exponential. We know what linear functions are. They're in the form of y equals mx plus b. Exponential are a times b to the x. Why is this type of function a good model for these data? Because it's doubling there is a common ratio, and that's the definition of an exponential function. So some sort of explanation similar to that will be good enough. Number 4, the population of a sample of bacteria triples every minute. If A is the initial population of the sample, Kim believes the equation y equals 3 times t to the a can be used to find the population after t minutes. Explain why Kim is correct or incorrect. So first thing, we should notice right away that Kim is incorrect, because when we look at an exponential function, a times b to the x, a is my initial value, b is my rate, and then x is x, obviously. So the equation that she wrote, 3 times t to the a, would mean that she's starting with 3 and she has a growth rate of t. Well, that's not right. She has an initial value of a and a growth rate of 3 because she's tripling. So she's incorrect because the coefficient, so that would be the a, should be a for the initial value, and 3 should be the growth rate. And the next part, if it's incorrect, what is the correct equation? Well, the correct equation would be y equals a times 3 to the t power. So we have an initial value of a in the population of bacteria. We're tripling, and it's taking us, we're tripling every minute, and t is the number of minutes. So number 5, how would the graph of y equals negative 5 to the x be shifted if it was changed to y equals 5 to the x plus 2? So shifting, we can shift up and down, we can reflect, we can compress, we can stretch. First thing I notice is that I have a negative 5 in the original equation, and I'm missing the negative. So that negative means that my graph is going to reflect. So the negative implies that the graph reflects over x-axis. Sometimes the vocabulary we use for this is it is a decreasing function, and it turns into an increasing function. So decreasing, the negative means it's going, the graph is going to look something like this. For the 5 to the x, it's going to be going up. So it goes from a decreasing function to an increasing function. And then the other thing we have to worry about is that plus 2. That plus 2 means the graph was shifted up 2 units. All right, number 6. The graph below represents f of x equals 3 to the x power. State the domain and the range for f of x. So we know that the domain, because we've been doing it all year, the domain is the x values, all the possible x values, and the range is the possible y values. So my domain, if I look at this, we have little arrows on both ends of the graph, which means my graph continues forever in both directions, and there's no holes, there's no places where my graph stops moving side to side. So my domain is negative infinity to infinity. In my range, the y values, I'm looking top to bottom. It looks like I can go up as far as I want, but when I go down on the graph, I never cross this x-axis. So my range is 0 to infinity, and we talked about in class why it's a parentheses. It's a parentheses because our graph can never actually touch 0. I can't ever equal 0. So we say it gets close to 0 but never actually touches it. Part B, sketch the graph of g of x, which is negative 3 to the x. We just talked about what this negative does. All it does is it flips our graph upside down. So we can take all these points that we can see on the original graph and just give them a negative y value. So points that we can tell where they're at, we can see where this point is. I can see this point, and I can see one more right up here. So it looks like I've got 0, 1, 1, 3, and 2, 9. If it's a negative x, I'm going to have 0, negative 1, 1, negative 3, and 2, negative 9. And then I'm just going to kind of sketch as best I can. I'm going to make sure I never cross that x-axis. Draw my little arrows, and there's my new function. And then how does the graph of g of x shift compared to f of x? Well, again, it's reflected over the x-axis. And in this case, we would say it changed from increasing to decreasing. Those mean the same thing, it's just different vocabulary. How did the domain and range change? Well, the domain, I still have the little arrows on both ends, so my domain is still negative infinity to infinity. And my range is, now instead of it being 0 to positive infinity, it's negative infinity until 0, because I can go as low as I want to on this graph, but I stop when I get to that x-axis again. Alright, moving along, part C, sketch the graph of h of x equals 3 to the x plus 2. So comparing it to the graph on the left, we have the same growth rate, but this plus 2 means that all my points are shifted up. I'm going to actually do this part right now since we're talking about shifted up 2 units. So I can do it very similar to the way I did the previous one. Take all these known values, 0, 1, 1, 3, 3, 9, or 2, 9, and just shift them up 2 units. So instead of being at 0, 1, I'm at 0, 1, and then up 2. So puts me at 0, 3. 1 used to be at 3, but I'm going to shift it up 2 to 5. And then 2 was supposed to be at 9, but I'm going to shift it up to 10, 11. It puts me right off the graph. And so now I can draw this line. And we got to be careful because this little horizontal line that we couldn't cross, that imaginary like 0 point, that also got shifted up 2 units. So now we have this imaginary horizontal line at 2 because it moved up 2 units. And when I graph, I get a picture like that. So how did the graph change? Well, it shifted up 2 units. How did the domain change? Well, domain still didn't change. So domain is still negative infinity to infinity. But the range now shifted from the original problem. Instead of going from 0 to infinity, now we go from 2 to infinity. And then part D, this one looks a little bit different. We didn't really cover these in class on this unit, but we have talked about those shifts with that x value when we did absolute value functions. So this says 3 to the x plus 2. So if we look at the other problems we've done, we've talked about a reflection with a negative value over here on the left. We've talked about vertical shifts if there was like a plus something out here, which there's not in this case. This x plus 2 up there, that's going to move my graph left to right. And if we remember from the absolute value unit, or the absolute value graphs, that plus 2 actually makes my graph move in the opposite direction. So my graph is going to shift. Plus 2 normally means right, but we're going to shift left 2 units. So all my points, all my original points are going to shift left 2 units instead of right 2 units. So that point that was at 0, 1 on the original graph, now I shift it left 2 units. My point that was at 1, 3, shift it left 2 units. My point that was at 2, 9, shift it left 2 units, and we get this. And now we draw our line, or our curve, and we get that guy. So it looks the same as the original problem over here on the left-hand side, It's just all the points have been moved left 2 units. How did the domain and range change? Well, once again, common theme, the domain does not change. All values still work, and my range, we didn't move up or down at all, so my range is still 0 to infinity, all with parentheses instead of brackets. All right, number 7, use the table to justify that y equals 3 times 1/2 to the x is exponential. Well, we already know it's exponential, but we're using the table just to show it. So we're going to plug in these x values into my function. And so my first one, 3 times 1/2 to the 0 is just 3. 3 times 1/2 to the first is 3/2, which is 1.5. 3 times 1/2 to the second power is 3/4, which is 0.75. And 3 times 1/2 to the third is 3/8, which is 0.375. And my common ratio, we should already know that just from the equation itself. My common ratio is 1/2. The justification, common ratio of 1/2 between all points. Number 8, using the table below, how does the function represented in the table change over equal intervals? So we have equal changes in x, we're adding 1, and we look at the outputs, 256 to 64 to 16 to 4. If we divide those, we notice that we're dividing by 4 each time. Well, dividing by 4 is the same as multiplying by 1/4. These are equivalent to each other. Dividing by 4 and multiplying by 1/4. So for equal intervals changing by 1 in the independent variable, which is x, the corresponding dependent value changes by -1/4. Well, that's not true. They didn't change by -1/4. We multiplied by a positive 1/4. Changing by -1/4 means that we would subtract 1/4. That's wrong. B, for equal intervals changing by 1 in the independent variable, the corresponding dependent variable changed by a factor of 1/4. That's what we're looking for. Factor is something we're multiplying by. Remember, we call it a common factor or a common ratio. And so B is my answer. C, once again, we're changing by -1/4. That means we're adding or subtracting that out. And D, I don't know why it's on there twice, but it's the same thing as B, so that's also correct. Part B, based on that change, what type of function is it? Well, if it has a common ratio, if we have something that we're multiplying by, it's got to be exponential, which is B. Number 9, using the graphs shown below, prove that each function is either linear or exponential. So obviously we know like g of x is linear. I hope we all know that because it's a line, it's not a curve. How do we prove it? Well, lines have a slope and they have a common slope. So we have 3 points that we can see. We have a point at -2, 3, a point at 0, 2, and we have another point down here at 2, 1. What we need to do is show that the slope from this point to this point is the same as this point to this point. So to prove our answer, we're going to say that I'm going to say M1, so that's my first slope, and you can label it if you want to. We'll call this M1, we'll call this part M2. So M1 is going to be 2 minus 3 over 0 minus -2. I just used the slope formula, y2 minus y1 over x2 minus x1. That's -1 over 2, which is -1/2, and M2. So now I'm going to use these 2 points, and that's going to be 1 minus 2 over 2 minus 0, which is -1 over 2, which is -1/2. Same thing. Those are equal, so we just proved that it is linear because we have the same slope between 2 points. Which function is exponential? Well, obviously that's got to be f of x. Prove that answer. So we know it's exponential if it has a common difference. So we need to show the common difference. So think back to what we did like on this problem here. We showed the common difference by dividing the outputs. So again, I'm going to find a couple points that I know. We've got 3 of them. We have a point at 2, 9. This point here was at 1, 3, and this point down here was at 0, 1. So if we think about like an input-output table, x, y, 0, 1, 1, 3, 3, 2, 9, sorry. We have consecutive inputs. Those are +1 each time. And my outputs are divide by 3. Divide by 3. So that I just proved right there that it's exponential because I have a common difference, or not common difference, I don't know why I said common difference up here. Common ratio. We have a common ratio of 1/3. All right, number 10, what is the equation for that table? So first I have to decide if it's exponential or linear or what it is. So I look at my inputs, -2, -1, 0, 1, 2. So they're consecutive. I don't have to worry about anything weird. And I look at my outputs. Am I adding by something every time? Well, I'm adding by 2 here, but I'm adding by 4 here, and I'm adding by 8 here. So +2, +4, +8. Can't be linear. Can't be. Because linear has to have the same addition every time. Is it exponential? Well, if it's exponential, I have to be able to multiply by the same thing every time. So that's going to be, let's see, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and 16 times 2 is 32. Yeah, it's exponential. So my equation for an exponential function we know is y equals a times b to the x. A is my initial value, and we find the initial value when x is equal to 0. So we're looking at this point, so that's 8 times b is my common ratio, and my common ratio was to multiply by 2, and we raise it to the x power. So my function is 8 times 2 to the x. 11. A ball is dropped from a height of 50 feet. It rebounds 2/3 of its height every time it hits the ground. Write a function that models the height of the ball over time. Well, that's going to be exponential again, because if it starts at 50 feet, so we're 50 feet here, the next one is 50 times 2/3 is the new height. The next height here is the previous one, so that's 50 times 2/3 times another 2/3, because it's 2/3 of that height. So my function is just y equals 50, which is my initial value, times 2/3 to the x, and x is the number of times it bounces. So on the 0 bounce, it's a height of 50. On the first bounce, it's 2/3 of 50, and so on. How would your function change if the ball were flat and only rebounded 1/8 of the height every time? Well, the only thing that changes, it still started at 50, but instead of bouncing 2/3 as high, it bounced 1/8 as high. And we would say that it is vertically compressed. Remember, compressed means it gets closer to the x-axis. So the original function up here might look something like that. The new function is it has a different growth rate, so it starts at the same point, but it's gonna be a little bit shallower. It's gonna take longer to do that. All right, number 12. Use the graph below. For the interval 0 to 10, which function appears to increase fastest as x gets larger? So we're just looking from 0 until 10. So I'm actually going to pull out a highlighter real quick so I can highlight just the part that I care about. I'm only looking from this little region right here, this yellow part, okay? So I just want to know which of those 4 graphs, F, G, H, and K, which one of them increases the quickest. They all start at the same point. Which one gets to this far right boundary quickest? Well, the one that gets there the quickest is, or the one that goes the furthest at that far right boundary, that's going to be this function, which is f. So f of x is the quickest. For the interval 10 to infinity, which function appears to increase fastest? So that's going to be from 10 to infinity. So we're going to go from that 10 and we're going to go to the right. So we got to be a little bit careful when we look at this. So they're all starting in different spots now, but we look at which one is increasing fastest, which one's getting taller quicker than everything else. K is staying pretty flat, H is getting taller quicker than K, but G is getting taller quicker than H and K, and F is going up as well. But look what happens right about here at this point. G is actually going to cross inside. That's a really bad drawing right there. But if I extend this line out, F is going to look like this, G is going to go up like this, and G actually crosses inside of F. So G is eventually going to get taller quicker. So G is the fastest one from 10 to infinity. 13, use a table or graph to place the functions in order from smallest to greatest. So I'm going to pull out the calculator here so we can take a look at what's going on. And alright, so I'm going to make a graph. Let's make that. Okay, so I'm going to add a page to my graph. I'm going to add a graph, and I'm going to type in each of these functions. 10 to the x. The next one is x cubed. The next one is 16x. The next one is 2x squared. And the last one is 3 to the x. And those are really difficult to see, so I'm actually going to change my window a little bit here. Menu, window settings. So my x, man. So I just want to know what happens when x increases. So I'm going to start at 0. I'm going to go to 7 because it looked like it was pretty small. Y min, they all look positive, so I'm going to go like -1 just so I can see it. And I'm going to make this like 20. See how that looks. Alright, so not great, but it should be good enough for us to see kind of what's going on. So they all kind of start at the same spot, approximately. I want to go the smallest to greatest as x increases. So the smallest one is going to be the linear function. It's going to increase the slowest. So this one all the way over here. As x gets big, it's going to stay like that, and everything else is going to kind of cross through. Even the ones over here on the green one, the pink one, and the red one, they're going to eventually get taller quicker. So my slowest one is the linear function, so that's c. My next slowest is going to be my quadratic function, this pink one, because it's still kind of flattening out. It's going to be a little bit quicker than the black one, but not much, so that's d. My next slowest is going to be, we can already see this green one, which is 3 to the x, and then the red one, which is x cubed. It looks like, let's see what happens when we make my window a little bit bigger. So window settings, let's make my Y max like 50. And we can see that green one starts to pass inside of the red one. So that's going to be x cubed is next, which is b. And then the last two that we have are the 10 to the x and the 3 to the x. And they're so far apart on the graph, it's hard to see them. But we know that 10 to the x has a growth factor that's 10, and 3 to the x has a growth factor that's 3. So the 3 has to come before the 10. So my order is C, D, B, E, A for order of smallest to largest. Go ahead and put this back. All right, 14. Based on the change per unit interval, choose an appropriate type of function to model the situation. So when I look at this, is it linear? All my hours increased by 1, but my number of bacteria are not changing at an even amount. We're not adding the same thing. In fact, it looks like we are multiplying by a third each time. And you can check it on your calculator. We in fact are multiplying by a third or dividing by 3, however you want to look at it. So my answer here would be it's exponential, and my justification, common ratio of 1/3. 15. What's the common ratio for the following exponential function? Consecutive inputs 0 through 5. My y values are 1.5, 6, 24, 96. So remember, we find the common ratio by dividing any two of those, and we get a common ratio of 4, multiplying by 4 each time. The justification, the justification would be 6 divided by 1.5 is 4, 24 divided by 6 is 4, 96 divided by 24 is 4, and you could do the rest of them if you really wanted to. All right, 16. A small company has an average monthly electricity bill of 8,000 kilowatt hours per year. Their 5-year plan calls for average monthly electricity to be reduced by 10% each of the 5 years. Identify the initial value, growth rate, growth factor, and equation. So the initial value, we started at 8,000 kilowatt hours. The growth rate is 10%, but that needs to be as a decimal, so that's 0.1. The growth rate, we're not actually growing, we're reducing. So we discussed in class that if you're growing, you would do 1 plus your growth rate, but since we're reducing, it's 1 minus my growth rate, which leaves me with 0.9. So my equation is going to be y equals 8,000 times 0.9 to the x. 17, you have an investment of 10,000. It grows 11% per year. What function represents the value? So again, we have an initial value of 10,000, which these all do. And it has a growth rate, or it grows 11% per year. So the growth rate is 0.11. And since we are actually growing, it's 1 plus 0.11 is my growth factor. And that's going to be A. 10,000 times 1.11 to the t. 18. The number of wolves in the wild is in the northern section of Coconino County is decreasing at a rate of 5% per year. Your environmental studies class counted 80 wolves in the area. Write a function representing the number of wolves. So initial value, 80. My B, we're decreasing at a rate of 0.5, so that's 1 minus, I'm sorry, it's a 5% decrease. So it's 1 minus 5%, which is 0.05 is a decimal, so that's 0.95. So we have an equation of y equals 80 times 0.95 to the x. Part B, after how many years will this population of 80 wolves drop below 50 wolves if this rate decrease continues? So we want to know where our function 80 times 0.95 to the x is equal to 15, or when does it pass 15 wolves? What value of x makes that happen? So you can start just plugging numbers in, which is fine. Not the best way to do it, but you certainly can. Or we can go to the calculator and graph these two halves of the function, the two sides, and see where they intersect. That's actually what I'm going to do. I'm going to go to my calculator, and calculator. All right, so we got our calculator. I'm going to make a new graph, and I'm going to put in my function 80 times 0.95 to the x, and I'm going to put in my other function of 15, and I see nothing on my graph because my window isn't set correctly. I'm going to go to window settings. Remember, we can also just double click. My pen gives me a really hard time when I do it. There, it actually worked that time. But I'm going to go 0, and we press tab, we go to the next value. 6.67 is definitely not tall enough because I need to be the function on the right, the 15 volts, that's like the minimum value, and we know the other one starts at 80, so I'm going to go to like 85 tab. Now we can start to see something. I definitely can't see enough over here. I'm going to go to like 40, and my y value, my minimum, I'm going to make it 0, and we get, oops, keeps grabbing the wrong thing. I'm just trying to grab that label, get it out of the way. There it is. All right, so there's my intersection point right there. So we just need to find it. Remember, we do menu, analyze graph, intersect, and we're going to put the dotted line left of that point we're looking for, right of the point we're looking for, and there is my intersection at 32.6 comma 15. So x equals 32.6. That's years. So it says, after how many years will this population of 80 wolf drop below 15? Well, at 32.6 years, it's exactly 15. So we could say after 32 years, or about 33 years. Either one of those would be appropriate answers. All right, last couple problems on the back page, very last page. 19. Each year, the local tennis club sponsors a tournament. Play starts with 128 participants. During each round, half the players are eliminated. So if we start with 128 after one round, we only have half those players left. What is the average rate of change between the first round and third round? So rate of change is slope. So we need to find the slope between the first and the third round. So we need points. So my first round is here. So round 1, there's 64 players left because we started with 128 and we cut that in half. My second round, I've got 232, and my third round, I'm down to 316. What we want is we want the slope from the first point to the third point. So imagine a line going through there. We want that slope. So we can count if we want to, or I'm going to use the slope formula. That's the quickest way to do it. So I'm going to have 16 minus 64 over 3 minus 1. And 16 take away 64 leaves me with negative 48 over 2, which is negative 24 players per year. So, not per year, per round. So it means each round, approximately on average, we're losing 24 players per round. We know that's not exactly true because we're cutting it in half, but that's what average rate of change tells us. 20 for these two functions, 3x plus 4, which is linear, and 2 to the x minus 5, which is exponential. Which function has the greatest rate of change over the interval 1, 6? Justify your solution. So again, rate of change, that's slope, and we have an interval 1 to 6. These are only x values. So we need points again. So we've got f of x over here. I'm going to put g of x over here, and I'm going to compare the slopes, just like we did up above, where we found the slope between those 2 points. we're going to find the slope between these 2 points, but it's between 1 comma something and 6 comma something. We need to find those somethings. So we have inputs. To find the outputs, we do 3 times 1 plus 4, which is 7, and 3 times 6 plus 4, which is 22. So we find that slope, which is 22 minus 7 over 6 minus 1. That's going to be 15 over 5, which is a slope of 3. So f of x has a rate of change of 3 from 1 to 6. G of x, same thing. I'm looking for 1 comma something and 6 comma something. So g of x is 2 to the first minus 5, which is negative 3, and 2 to the sixth minus 5, which if we use our calculator we get 59. So that slope is 59 minus negative 3 over 6 minus 1, which is 62 over 5, which is, I think it's 12.4. So obviously that rate of change is greater than the other one, so we can say g of x has a greater rate of change from 1 to 6. And that's the end of our review. Study well.